Hey, welcome back to Short Text 331. Today, we're going to talk about a very special unitary matrix. So let's review the properties of unitary matrices. If you recall, unitary matrices are defined as those matrices such that the inverse is equal to the dagger, and the dagger is just the transposed complex conjugate. So suppose we have then a matrix of size n by n, and we're going to have matrix elements I and j, with I and j going from 1 to n. And so this identity that the inverse is the dagger simply means that the elements of U inverse ij are the same as uji complex conjugate. So it's a complex conjugate of the transpose. That's a really nice property. Imagine how easy it is to calculate an inverse. Just flip your indices, complex conjugate, and you're ready to go. And this implies a number of properties of the rows and the columns, just having this, as we will review now. So suppose that we take the columns of U as vectors, then it turns out that those vectors are orthonormal. They're mutually orthonormal. And the same is true for the rows, by the way. So suppose we do that. We take the columns to fix ideas. And so taking the columns of U amounts to defining our vectors like this. So we have the kth vector, element I, that would be given by the element ik of U. So then I runs through the various rows, and k is a fixed column, and so it's a fixed vector, and so that populates the vector v sub k. And as you vary k from 1 to n, the claim is that those various vectors defined in that way, defined like this, are mutually orthonormal. And again, those are the columns, but the same will apply for the rows. And so let's see how that works out. Well, it turns out that we know that U inverse U, which is also U dagger U, is equal to the identity matrix. And so that means that the elements of U inverse U have to be delta AB if we calculate them in this way. So delta AB is the Kronecker delta, is 0 if A is different from B, and it's 1 if A is equal to B. And the statement that U inverse U is the identity then is the statement that delta AB is equal to the sum over I of the AI element of U inverse times the IB element of U. And so sum over I of U inverse AI, UIB, but it turns out that we know that U inverse AI is simply U star IA, and so we use the property of unitarity at that point, and that is precisely what we have up here for V sub B in this case and V sub A star in this case. So it's where I wrote here. So we can replace UIA star as the 8th column of U elements of I, and the bth column of U elements of I again. And for sum over I, what we have here is an inner product. That is an inner product of those two vectors, VA with V sub B. This inner product summing over the elements of the vector with the star on the first component of the inner product is what we defined in the video on the inner product. And if you haven't seen the video, then you can go back quite a few videos back. You can go and check it out, and then you'll see that this is how we define the conventional inner product. It's not the only way to define an inner product, but it works in this particular case to interpret that as an inner product. And so that the statement that this whole chain of identities is equal to delta AB is simply the statement that VA with VB are going to be orthogonal to each other if A is different from B. In other words, different columns of the matrix U are mutually orthogonal to each other, and if A is equal to B, then we have that the result is 1, and that gives us the normality condition, and so we say that these columns are mutually orthonormal. Now, it turns out that not only is U inverse U equal to the identity, but also U inverse. And if you go through the same song and dance and interpret U inverse as U star transposed, but in this case using U and U inverse instead of U inverse U, then you arrive at a different property, the property of completeness, which we saw in the previous video and the one before that. This was mentioned in the last couple of videos. Then you see that this delta AB tells us that the sum over k over different vectors, and the same vector but different elements of the same vector gives us delta AB, and that's a statement of completeness. So it's not really an inner product between the two vectors, and it's if you think of these vectors as being the columns, but rather it's a different kind of statement. That is what we call completeness. The fact that if you sum over all the vectors and put here different elements of those vectors, then you get 0 if you're talking about different elements, and you get 1 if you're talking about the same element. Now, the role of this whole explanation here is reversed, or is transposed, if you want, if we take the rows instead of the columns. If we do that, then the statement about U inverse U gives us completeness, and the one coming from U inverse gives us orthonormality. So the point is then the rows and the columns are mutually orthonormal, and those imply the property of orthonormality and completeness when you consider what happens with U inverse U and U inverse. Now, another property that's interesting about unitary matrices is that the determinant of any unitary matrix has to be of the form e to the I alpha for some real quantity alpha. This alpha has to be real. I should have said here alpha belongs to the reals. Here I is the imaginary unit, is that number, that complex number such that I squared is -1. And this e to the I alpha is simply a way to parameterize a complex number of unit magnitude. In other words, the determinant of U is typically going to be a complex number. It's going to involve complex elements in U, but we know that it's the magnitude of the determinant has to be 1. And by the way, the reason this is a parameterization of the unit magnitude complex number is simply that the magnitude of e to the I alpha is 1. Here I compute the magnitude, I should say square, e to the alpha squared is cosine squared plus sine squared of alpha by using the Euler's formula shown here, which we'll come back to in a future video on complex numbers, and that is just 1 by the Pythagorean theorem. And so we know that is true, that this is a good parameterization of a number of unit magnitude. So there's some alpha then that satisfies that some real alpha such that e to the alpha is the determinant of whatever matrix, unitary matrix you're talking about. And you can see that that has to be the case, that the magnitude of the determinant of any unitary matrix is 1, because we know that the determinant of U inverse U is 1. It's just the determinant of the identity, which is 1. But by the same trick we worked with before, which is the main property of unitary matrices, U inverse is U dagger. And so we go from here to here. The determinant of U inverse U, which is 1, is the determinant of U dagger U, which we can separate now. This matrix is square. We're allowed to do that. Is the determinant of U dagger, determinant of U. But the determinant of U dagger, turns out, is just a complex conjugate of the determinant of U. And so we have a complex number, complex conjugate times the complex number itself. So that's the magnitude square of the complex number. And that gives us that then the magnitude square of our number has to be 1, which means that the magnitude of our number has to be 1. And so if the magnitude of the complex number is 1, then it must be that there's some alpha that gives us when you combine it and in this form and say e to the I alpha, that's the determinant of our matrix. It turns out unitary matrices form a group also under multiplication. That group is usually called UN. There will be future videos on groups and other algebraic structures, but the essential property that you need for a group under multiplication in this case is that multiplication is closed. That is that if U1, U2 is unitary, if U1 and U2 are separately unitary, then U1 and U2 is also unitary. And that is indeed the case. If you take U1 and U2 and you take the dagger of U1, U2, you get U2 dagger, U1 dagger. But it turns out that's U2 inverse, U1 inverse by virtue of U1 and U2 being separately unitary. And we know that we can regroup these as U1, U2 inverse. And so this tells us then that indeed, if U1 and U2 are themselves unitary, then the product of those two matrices is. Now, usually U1 and U2, when multiplied together, will give different results if you do U1, U2 or U2, U1. So the order of multiplication matters typically for unitary matrices. In fact, the only case where it doesn't matter is if n is 1, if you're just talking about numbers. But generally speaking, if you are looking at n equal to 2 or greater, then the product of two unitary matrices will not be commutative. And that means that this group will then be non-abelian. That's what we call a non-abelian group. A group where the composition property or the multiplication property is not commutative. So all of these properties and more you get just by virtue of U being unitary. So far we haven't really done anything too special in any particular way. We just talked about unitary matrices. So what is this very special unitary matrix that I talked about in the title? This is a very peculiar matrix that has matrix elements that take this form. Now I'm going to call this unitary matrix F because it's associated with a fast Fourier transform. well, just with the Fourier transform in general. In fact, the discrete Fourier transform, and the matrix elements of F, J, K are 1 over square root of n, where n is the size of our matrix, and e to the I is the complex, the imaginary unit, times 2 pi divided by n times j times k, where again j and k are the elements of my matrix, and so they go from 1 to n. You could also actually make j and k go from 0 to n minus 1, and this would work just as well. It doesn't have to be from 1 to n, it just have to be an interval of size n in the natural numbers. And probably I think if you use negative numbers, it would work as well. You can use integers as long as there's an interval of size n in the integers. So you cover from 1 to n, or from 0 to n minus 1, and so on. And this is interesting because it can be written as some number to the power j times k. That number being, of course, e to the I 2 pi over n. And this gives you a very peculiar structure, which turns out to allow for extremely efficient algorithms, and as I will say next. And this is the root of what we call the fast Fourier transform, which is a particular type of transformation that allows to diagonalize a very large class of important matrices. Which important matrices? Well, it turns out that matrices that represent differential operators, like the second derivative and such, typically can be diagonalized with a transform of this form. So with a unitary matrix, like we've seen before, that unitary matrices can be used for normal matrices to diagonalize those normal matrices. Then if you do it in this way, so if you sandwich your matrix with two unitary matrices that represent the eigenvectors of your matrix, then you can obtain the diagonal that contains all the eigenvalues of your matrix. So this is what we call the operation of matrix diagonalization, and it turns out that for, like I said, for a large class of important matrices that typically represent differential operators, like the second derivative, then this operation can be done very quickly and very efficiently for the reason that due to the reason of having this type of structure for our matrix. This has been known for a very long time, by the way. I think already Gauss knew about this, the possibility of doing this very efficiently, but it was rediscovered by multiple people in history, and it was shown that if you want to do this operation with just any matrix and you don't pay attention to this particular efficiency that you have for this particular case, the particular class of matrices and the particular shape of this unitary matrix, then doing this operation takes order n cubed operations in general. So doing this whole sandwiching of the matrix with two unitary matrices to obtain the diagonal form will cost n cubed operations. But it turns out that if you're doing this for a particular matrix like this one, like represent the differential operator, which can be diagonalized with a discrete Fourier transform of this kind, then that can be done in order n squared log n. Of course, you can do it inefficiently in the old way and just multiply the matrices and obtain the final result. That would be the slow Fourier transform. It would not be the fast Fourier transform. That would cost you order n cubed. But it turns out that this can be done in order n squared log n for f using the fast Fourier transform algorithm, which is actually a whole class of algorithms. It's not just one algorithm. You can see that this would make a huge difference if your matrix is very large. Okay, so for example, if your matrix is of size 10 by 10, then we're talking about something order of 1,000, and here we're talking about something order of 100 times something else. And so you start to see that the difference becomes substantial. And that's it. That's all I have for you today. I hope you enjoyed this video. We will continue talking about Fourier series and Fourier transforms and unitary matrices and groups and all that in future videos. And if you like this series, please like and subscribe. If you need a tutor in physics or math in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a comment in the comment section below. Until next time.